You know all the music that's just everywhere in your life? A pop song on the radio, that epic movie score, a symphony. It all just kind of washes over you, feeling so natural. But underneath it all, there's this hidden architecture, a secret set of rules. So, let's pull back the curtain and explore that hidden world.
I mean, it's the most basic question, right? Why is it that one chord can give you actual goosebumps, but another one just sounds off and makes you wince? We've all felt it. But here's the thing. It's not magic. It's this incredible blend of art, history, and the actual science of how our brains process sound.
So the official word for what we're talking about, it's harmony. And at its most basic, it's just the art of stacking different notes together to make a chord, and then stringing those chords together in a way that makes sense. You can think of it as the vertical part of music, what's happening up and down at any single moment in time. Okay, to really get harmony, you have to understand that it's all built on these two fundamental opposing forces. This is the push and pull that gives music its emotional weight. It's this constant dance between tension and release.
And here they are, the two main players, consonance and dissonance. On one side, you have consonance. These are the sounds that feel pleasant, stable, relaxed. It's that feeling of, we've arrived. Then you have dissonance. This is the opposite. It feels tense, a little rough, unresolved. It's the cliffhanger that leaves our brains itching for a solution.
So you might be thinking, okay, simple. Dissonance is bad, consonance is good. But actually, the secret ingredient to great music is dissonance. The best music doesn't just avoid those tense moments, it uses them. It builds up that tension on purpose, taking you on a journey, so that when the relaxed, consonant moment finally hits, it feels earned. It's that beautiful, satisfying release.
So how do you actually build those nice, relaxed consonant chords? Well, in most of the music we hear, there's a pretty simple recipe. It's called tertian harmony. Basically, you start with one note, the root. Then you stack another note, what's called a third, right on top of it. And then you do it again. You stack another third on top of that. Boom. That simple three-note stack gives you a triad, the most fundamental chord in Western music.
And this is really where the magic happens. The space between any two notes, the interval, has its own distinct flavor. A perfect fifth feels incredibly stable and open. A major third sounds sweet and happy. But then you get to something like a minor second, and it's super clashing and tense, and the triton is famously unstable. This is the composer's emotional toolkit, letting them pick and choose intervals to build chords that guide how we feel.
Okay, so we've got the what down. We know what sounds good together. But that just leads to a way deeper question. Why? Why do these rules work? Is it just something we've all agreed on? Something we've learned from our culture? Or is there something deeper going on? Something hardwired into our biology?
And to answer that why, we have to leave the concert hall and step into the laboratory. We're entering the world of psychoacoustics, the study of how our brains actually perceive sound. Because as it turns out, harmony isn't just in the sound waves. It's something that's actively created inside our own heads. So researchers have found that our brain's preference for consonants really boils down to three main things. First, there's smoothness. Our brains just don't like the feeling of rough sounds. Second, harmonicity. Our brain is a pattern-finding machine, and it loves it when sound waves have simple, neat mathematical relationships, just like things found in nature. And third, well, it's just plain old familiarity. We grow to like the sounds we've heard the most.
Let's dig into that first one, roughness, because it's pretty mind-blowing. It's not just a poetic description. It is a real physical sensation of harshness that happens when two sound waves are so close in their frequency that they literally start fighting with each other as your ear tries to process them.
And here is where it gets absolutely wild. Deep inside your ear, you have these tiny receivers that are tuned to specific frequencies. Think of them like swim lanes, where each lane is a critical bandwidth. When two notes are far apart, they vibrate in their own separate lanes, no problem. But when they're too close, like that tense minor second, their sound waves spill into the same lane. They physically interfere with each other, creating this rapid fluttering or beating sensation that your brain interprets as dissonance. It's not just a matter of opinion, it's physiology.
So if harmony is built on these predictable rules of physics and biology, that raises a really modern question. Can we teach a machine to understand it? Can an algorithm listen to a piece by Bach and actually figure out the harmony?
This is the new frontier. Researchers are trying to design AI that can do more than just hear notes. They wanted to analyze a piece of music and map out its entire harmonic journey, just like a music theorist would. But, as you can imagine, teaching a computer to listen with that kind of understanding is unbelievably hard.
See, when you or I listen to Bach, we hear drama, melody, emotion, a story. A computer? It just sees a massive, chaotic stream of data points: pitch, duration, volume, on and on. The whole challenge is teaching the machine how to find the meaningful patterns, the real harmony, hidden inside all that noise.
And that really brings us to the single biggest problem they face. In any piece of music, some notes are fundamental to the structure, while other notes are just fancy decorations. The computer has to learn to tell the difference.
Let's use an analogy. Think of a song as a house. The chord tones, those are the foundation, the pillars, the load-bearing walls. They are the essential structure holding the whole thing together. Then you have the non-chord tones. These are the paint on the walls, the art, the furniture. They're what make the house beautiful and unique, but they aren't holding up the roof. Our brains understand this difference intuitively. A computer just gets lost.
But they're making some amazing progress. So how good are they at it? Well, in a recent breakthrough, a new algorithm was tasked with analyzing the incredibly complex harmonies of Bach. It correctly identified the underlying harmony 55% of the time. Now, I know what you're thinking. 55% is a failing grade. But for a task this complex, that's actually a monumental leap forward. It means we are, slowly but surely, teaching machines the art of listening.
So, we've gone from music theory to human biology to artificial intelligence. Where does that leave us? What is harmony in the end? Is it art? Is it science? Or is it something else?
And the beautiful truth is that it's not an either-or question. It's an and question. Harmony is the exact place where art and science intersect. The very techniques artists have been using for centuries are deeply connected to the physics of sound and the wiring of our own ears. And now, the computer algorithms of tomorrow are starting to learn that same ancient language.
Which leaves us with one last big thought to chew on. If the very foundations of what sounds good are basically written into the laws of physics and our own DNA, then where does the human art part really come in? Maybe the true genius isn't in following the rules. Maybe it's in knowing precisely how and when to break them.